At the end of the 19th century, physics appeared complete. For more than 200 years, the framework built by Isaac Newton had guided scientists with astonishing success. Newton's laws of motion described how objects moved on Earth and in the heavens. His law of universal gravitation explained the fall of an apple and the orbit of the moon with the same elegant mathematics. The universe seemed orderly, predictable, and governed by absolute principles. Space was fixed and unchanging. Time flowed uniformly everywhere, like a universal clock ticking in perfect rhythm across the cosmos. In this classical world, if you knew the position and velocity of every object, you could calculate the entire future of the universe. The cosmos functioned like a perfectly engineered machine. This mechanical picture was so powerful that many physicists believed only minor details remained to be filled in. The grand structure of nature, they thought, had already been uncovered. Yet beneath this confidence, subtle tensions were growing. One major development came from the study of electricity and magnetism. During the 1860s, the Scottish physicist James Clerk Maxwell unified electricity and magnetism into a single theory. His equations showed that light itself is an electromagnetic wave. This was a monumental breakthrough. Light was no longer mysterious. It was a vibration of electric and magnetic fields traveling through space. However, Maxwell's equations contained a surprising prediction. Electromagnetic waves move at a fixed speed, approximately 300 kilometers per second. This speed emerged naturally from the mathematics. It was not relative to anything. According to Maxwell's theory, light traveled at this speed in a vacuum, period. But this raised a serious problem. In Newtonian mechanics, velocities are relative. If you walk forward on a moving train, your speed relative to the ground is the sum of your walking speed and the train's speed. Motion simply adds up. Scientists assumed light should behave in the same way. If you shine a flashlight while moving, shouldn't the light travel faster relative to someone standing still? To resolve this issue, physicists proposed the existence of a mysterious substance called the ether. They imagined space was filled with an invisible medium through which light waves propagated, much like sound waves travel through air. The ether was thought to be stationary and absolute, providing a universal frame of reference. Light's constant speed would then make sense relative to this ether. If the ether existed, Earth must move through it as it orbited the Sun. This motion should create an ether wind, affecting the measured speed of light depending on direction. To detect this effect, two American physicists, Albert A. Michelson and Edward W. Morley, conducted an extraordinarily precise experiment in 1887, known as the Michelson-Morley experiment. They designed an instrument capable of measuring tiny differences in the speed of light along different directions. If Earth were moving through the ether, the speed of light should vary slightly depending on whether it traveled with or against the ether wind. The result, however, was shocking. They detected no difference at all. Light's speed appeared identical in every direction. This null result deeply troubled the scientific community. If the ether existed, why could it not be detected? If it did not exist, how could light maintain a constant speed? The foundations of classical physics began to tremble. At the same time, other puzzles were emerging. Studies of blackbody radiation revealed discrepancies between theoretical predictions and experimental observations. Classical physics could not accurately explain how heated objects emitted light at different frequencies. According to classical theory, energy should be emitted continuously and in unlimited amounts at high frequencies, a prediction that clearly contradicted reality. In addition, experiments with fast, moving electrons hinted at unexpected behavior. Measurements suggested that mass might vary with velocity, something Newtonian mechanics did not anticipate. The neat, orderly universe was showing signs of strain. Despite these anomalies, many physicists attempted to preserve classical assumptions. Some proposed increasingly complex explanations to save the ether concept. Others modified equations slightly, hoping to reconcile theory with experiment. But these solutions often felt artificial, like patching cracks in a structure whose foundation was unstable. The deeper issue was conceptual. Newton's framework assumed absolute space and absolute time. There was a universal now, shared by all observers. Measurements of length and duration were thought to be the same for everyone, regardless of motion. Yet Maxwell's equations and the failed ether detection suggested something was fundamentally wrong with this picture. The crisis was not merely technical, it was philosophical. If the speed of light was truly constant for all observers, then the simple addition of velocities could not hold universally. If the ether could not be found, perhaps there was no absolute frame of reference at all. But abandoning absolute space and time would mean overturning centuries of deeply held assumptions. By the turn of the 20th century, physics stood at a crossroads. On one side was the powerful, successful edifice of classical mechanics. On the other side were experimental results that refused to fit neatly into that structure. The confidence of the 19th century was giving way to uncertainty. It was in this atmosphere of tension and unresolved questions that a young patent clerk named Albert Einstein began to rethink the problem from first principles. Instead of trying to detect the ether or modify Maxwell's equations, he asked a radical question. What if the difficulty lies not in electromagnetism, but in our assumptions about space and time themselves? The crisis of classical physics was not a sudden collapse, but a gradual realization that the old framework could no longer accommodate new discoveries. The stage was set for a revolution. The mechanical universe of Newton, once thought complete and final, was about to be reshaped in ways no one had imagined. In 1905, when Albert Einstein published his paper on the electrodynamics of moving bodies, he did not begin with complex mathematics. He began with two simple, bold statements. These two principles would become the foundation of special relativity. They were not derived from elaborate experiments conducted by Einstein himself. Instead, they were logical responses to the deep contradictions troubling physics at the time. From these two postulates, an entirely new understanding of space and time would emerge. The first principle states that the laws of physics are the same in all inertial frames of reference. An inertial frame is one that moves at a constant velocity, neither accelerating nor rotating. This idea was not entirely new. In fact, it echoes a concept first clearly articulated by Galileo Galilei centuries earlier. Galileo imagined being inside a smoothly sailing ship. If the ship moves at constant speed, experiments performed inside dropping a ball, watching fish swim in a bowl, would behave exactly as they would if the ship were at rest. There would be no experiment that could reveal whether you were moving steadily or standing still. Isaac Newton incorporated this idea into classical mechanics. According to Newton, motion at constant velocity is relative. There is no preferred inertial frame. The laws of motion apply equally whether you are standing on Earth or gliding smoothly in a train. Einstein accepted this principle completely, but he extended it further. He insisted that not only mechanical laws but all laws of physics, including those governing electricity and magnetism, must hold identically in every inertial frame. There could be no special rest frame for electromagnetic phenomena. This was a decisive move because earlier physicists had assumed that Maxwell's equations might only be strictly valid in the frame of the ether. By declaring that all physical laws are the same in every inertial frame, Einstein eliminated the need for a preferred reference frame. The universe, according to this view, does not privilege any particular state of uniform motion. If you are in a spaceship moving at constant speed, the laws of physics you observe are identical to those observed by someone at rest on Earth. No experiment confined within your spaceship can reveal your constant velocity. The second postulate is even more striking. It states that the speed of light in a vacuum is the same for all observers, regardless of the motion of the source or the observer. This idea directly confronts everyday intuition. In daily experience, speeds add together. If you run forward in a moving train, your speed relative to the ground is the sum of your running speed and the train's speed. Classical physics assumed light should behave the same way, yet experiments, especially the famous Michelson-Morley experiment, showed no variation in the speed of light due to Earth's motion. Maxwell's equations, developed by James Clerk Maxwell, predicted a fixed light speed determined by fundamental constants of nature. Einstein took this constancy seriously and elevated it to a universal principle. To grasp how radical this is, imagine a train moving at half the speed of light. A passenger inside turns on a flashlight in the direction of motion. According to classical reasoning, an observer standing still beside the tracks should measure the light's speed as the train's speed plus the speed of light. But Einstein's second postulate says this does not happen. Both the passenger and the observer by the tracks measure the same speed for the light, approximately 300 kilometers per second. This constancy cannot be explained by ordinary velocity addition. Something else must adjust. Einstein realized that if the speed of light remains constant for all observers, then measurements of time and space themselves must change depending on motion. Rather than abandoning the constancy of light, he abandoned the idea that time and length are absolute. The two postulates together create a powerful logical structure. The first removes any privileged inertial frame. The second asserts that light's speed is invariant. Combined, they demand a profound revision of classical concepts. One immediate consequence is the relativity of simultaneity. In classical physics, if two events occur at the same time for one observer, they occur simultaneously for everyone. But under Einstein's postulates, simultaneity depends on the observer's motion. Consider two lightning strikes hitting opposite ends of a moving train. An observer standing on the ground might see the strikes occur simultaneously. However, an observer on the train, moving toward one strike and away from the other, may perceive them at different times. Both perspectives are correct within their respective frames. This is not an optical illusion. It arises from the fundamental structure implied by the two postulates. If light's speed is constant for all observers, then differences in motion must alter how time is measured. Another consequence is time dilation. If two observers are moving relative to one another, each will measure the other's clock as ticking more slowly. This is a direct mathematical result derived from the two principles. Similarly, lengths contract along the direction of motion. These effects are not arbitrary distortions. They are necessary adjustments that preserve the invariance of light speed. What makes the two postulates so remarkable is their simplicity. Einstein did not propose elaborate mechanisms or hidden forces. He proposed two clear statements about symmetry and invariance. From them flowed an entirely new geometry of spacetime. In essence, the first principle tells us that the laws of nature are democratic. No inertial observer is special. The second tells us that the speed of light is a universal constant, woven into the fabric of reality. Together, they form the logical heart of special relativity. The power of these ideas lies in their inevitability. Once accepted, they force us to abandon the comforting absolutes of Newtonian space and time. They reveal a universe where measurements of duration and distance depend on motion, yet the underlying laws remain perfectly consistent. From just two postulates, Einstein transformed physics. He showed that by rethinking our most basic assumptions, we could resolve the crisis facing classical theory and uncover a deeper, more elegant structure of the universe. For centuries, time was considered the most stable and unquestioned element of reality. It flowed steadily, uniformly, and independently of everything else. Whether in the heavens or on earth, whether one was standing still or traveling at great speed, time was assumed to tick at the same rate for everyone. This belief was deeply rooted in the physics of Isaac Newton, who described time as absolute, flowing equably without relation to anything external. In Newton's universe, time was a universal stage on which events unfolded. When Albert Einstein introduced special relativity in 1905, one of the most shocking consequences of his theory was that time is not absolute. It does not flow identically for all observers. Instead, time depends on motion. It stretches and contracts depending on how fast one moves relative to another observer. This phenomenon is known as time dilation. To understand how Einstein reached this conclusion, we must recall one of his central insights. The speed of light in a vacuum is the same for all observers, regardless of their motion. This principle, combined with the idea that the laws of physics are identical in all inertial frames, forces a radical reconsideration of time. Imagine a simple thought experiment. Consider a light clock, a device made of two mirrors facing each other, with a pulse of light bouncing back and forth between them. Each round trip of the light pulse marks one tick of the clock. For an observer at rest relative to the clock, the light travels straight up and down between the mirrors. The distance is fixed, and since the speed of light is constant, the time between ticks is constant. Now imagine that this clock is placed inside a spaceship moving at a very high speed relative to an observer standing still outside. From the perspective of the stationary observer, the spaceship is moving sideways. Therefore, the light inside the clock does not travel straight up and down. Instead, it traces a diagonal path because while the light is moving between the mirrors, the entire spaceship is moving horizontally. Here is the crucial point. The speed of light must remain the same for both observers. Since the stationary observer sees the light traveling a longer, diagonal path, and since its speed is unchanged, the time it takes to complete one tick must be longer. In other words, from the stationary observer's perspective, the moving clock runs more slowly. This is time dilation. A clock in motion ticks more slowly than a clock at rest relative to an observer. The faster the relative motion, the greater the time dilation. At everyday speeds, this effect is incredibly small and unnoticeable. But as speeds approach the speed of light, the effect becomes dramatic. It is important to understand that this is not a mechanical malfunction of the clock. It is not that gears are slowing down or that some physical resistance is interfering. The slowing of time affects all processes equally: mechanical clocks, biological aging, atomic vibrations, even the beating of a heart. Time itself is stretched. One of the most famous illustrations of time dilation is the twin paradox. Imagine identical twins. One remains on Earth, while the other travels on a spaceship at nearly the speed of light and then returns. According to special relativity, the traveling twins' clock runs more slowly during the journey. When the twins reunite, the traveling twin is younger than the one who stayed behind. This scenario may sound like science fiction, but it follows directly from Einstein's equations. Time does not pass at the same rate for everyone. Motion alters the flow of time. Time dilation has been experimentally confirmed many times. In the mid-20th century, precise atomic clocks were placed aboard fast-moving airplanes and compared with identical clocks left on the ground. The airborne clocks lagged slightly behind, exactly as predicted by special relativity. Even more striking evidence comes from subatomic particles called muons. These particles are created high in Earth's atmosphere and have extremely short lifetimes. According to classical expectations, most of them should decay before reaching the surface. Yet large numbers are detected at ground level. The reason is time dilation. From our perspective, their internal clocks run more slowly as they travel at speeds close to that of light. The implications of time dilation are profound. It means that there is no universal now shared by all observers. Two people moving relative to each other will not agree on the duration between events. Each observer's measurement of time is valid within their own frame of reference, but there is no absolute clock governing the entire universe. This leads to the relativity of simultaneity. Events that appear simultaneous to one observer may not be simultaneous to another moving observer. If two lightning bolts strike at opposite ends of a train track, a person standing midway between them may see the flashes at the same time and conclude they occurred simultaneously. However, an observer on a moving train may see one flash before the other and conclude they were not simultaneous. Both observations are correct within their respective frames. The loss of absolute time challenges our deepest intuitions. We experience time as a steady progression from past to future. It feels universal and unchanging. Yet Einstein showed that time is woven together with space into a single four-dimensional structure known as spacetime. The separation between time and space depends on motion. What one observer measures as a difference in time, another may measure partly as a difference in space. The relativity of time does not mean chaos or inconsistency. The laws governing these changes are precise and mathematically exact. The time dilation formula allows us to calculate exactly how much slower a moving clock will tick compared to a stationary one. The structure is elegant and internally consistent. Einstein's insight transformed time from a rigid, absolute backdrop into a dynamic dimension intertwined with motion. It revealed that the universe is far stranger than classical physics had imagined. Time is not an independent river flowing identically everywhere. It is flexible, dependent on the observer's state of motion. In realizing this, humanity crossed a conceptual boundary. The comfortable certainty of Newton's absolute time gave way to a universe where duration itself depends on perspective. Yet paradoxically, by accepting this relativity, physics gained deeper unity and coherence. The constancy of the speed of light remained intact, and the laws of nature became fully consistent across all inertial frames. Thus, the relativity of time stands as one of the most astonishing and beautiful consequences of special relativity. a reminder that even the most familiar aspects of reality can conceal extraordinary truths. If time could stretch and slow down depending on motion, as special relativity revealed, then space itself could not remain untouched. The same principles that forced us to abandon absolute time also required us to reconsider the nature of distance and geometry. In the classical world of Isaac Newton, space was fixed and rigid. A meter was a meter, regardless of who measured it or how fast they were moving. But once Albert Einstein accepted that the speed of light is constant for all observers, the structure of space itself had to change. One of the most remarkable consequences of this realization is length contraction. According to special relativity, an object moving at high speed relative to an observer will appear shorter along the direction of motion than it does at rest. The faster the object moves, the more pronounced the contraction becomes. At everyday speeds, this effect is far too small to notice. But as velocity approaches the speed of light, contraction becomes significant. To understand why this must happen, we return to the constancy of the speed of light. Imagine a long spaceship traveling at an enormous velocity past a stationary observer. Inside the spaceship, a passenger measures its length using a ruler at rest relative to the ship. To them, nothing unusual occurs. The ship's length is perfectly normal. But the observer standing still outside must measure the ship's length differently. Measuring length requires determining the positions of both ends of the object at the same time. However, special relativity teaches us that simultaneity itself depends on motion. Two events that are simultaneous in one frame of reference may not be simultaneous in another. Because of this relativity of simultaneity, the stationary observer's measurement of the ships in points occurs under different time conditions than those of the passenger inside the ship. When the mathematics is worked out, the result is unavoidable. The moving ship's length is shorter in the direction of motion from the perspective of the stationary observer. This is not a visual illusion caused by perspective. It is a genuine physical contraction predicted by the geometry of spacetime. Just as time dilation ensures that the speed of light remains constant in all inertial frames, length contraction plays a complementary role. If moving clocks tick more slowly, moving rulers must also shrink. These two effects are intertwined, preserving the consistency of physical laws. This discovery leads to a deeper and more revolutionary insight. Space and time are not independent entities. They form a unified structure known as spacetime. Before Einstein, space was considered a three-dimensional arena, and time was a separate dimension flowing independently. After special relativity, they became inseparable aspects of a single four-dimensional continuum. The unity of space and time was later expressed elegantly by the mathematician Hermann Minkowski, who had once been Einstein's teacher. Minkowski reformulated special relativity in geometric terms, showing that events in the universe can be described as points in four-dimensional spacetime. In his famous words, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." In spacetime, what one observer measures as a difference in space, another may measure partly as a difference in time. The separation between events depends on the observer's motion. Yet there exists a deeper invariant quantity, the spacetime interval, that remains constant for all observers. This invariant replaces the old absolutes of space and time with a new, unified structure. To see how profoundly this reshapes our understanding, imagine two observers moving relative to each other. Each carries a measuring rod and a clock. Each sees the other's rod as contracted and the other's clock as ticking more slowly. These reciprocal effects might seem paradoxical, but they are consistent within the framework of spacetime geometry. There is no contradiction because there is no absolute frame from which one can declare a single true length or duration. Length contraction also explains certain experimental observations in particle physics. Consider HICE, bead particles created in accelerators. From our perspective, they travel enormous distances within extremely short lifetimes. From the particle's own frame of reference, however, the distance to be traveled is contracted. The journey appears shorter, allowing the particle to reach detectors before decaying. This mutual consistency between time dilation and length contraction demonstrates the internal harmony of special relativity. The merging of space and time changes not only measurements, but also our philosophical outlook. In the classical world view, the present moment was universal. Everyone shared the same now, but in spacetime, simultaneity depends on motion. There is no single cosmic present slicing cleanly across the universe. Events that are simultaneous for one observer may occur in different temporal orders for another. This challenges our intuitive sense of reality. We experience space as extended and time as flowing, but special relativity reveals that these experiences depend on our state of motion. The deeper reality is spacetime, a four-dimensional fabric in which events are woven together. Importantly, these effects become significant only at velocities close to the speed of light. In everyday life, where speeds are tiny compared to light speed, length contraction and time dilation are negligible. This is why Newton's mechanics works so well for ordinary situations. Special relativity does not overthrow classical physics entirely. It refines it, showing that Newton's laws are approximations valid at low speeds. Yet conceptually, the shift is immense. Space is no longer rigid and absolute. Time is no longer universal and uniform. Instead, both are flexible and interconnected. Motion reshapes them in precise, predictable ways. Through the recognition of length contraction and the unity of space and time, Einstein revealed that the universe possesses a deeper geometric structure than previously imagined. What once seemed like separate dimensions are now understood as facets of a single continuum. In this spacetime framework, the laws of physics achieve a new symmetry and elegance. The rigid stage of Newtonian space has dissolved. In its place stands a dynamic fabric where distances shrink, clocks slow, and measurements depend on perspective, yet the underlying reality remains consistent and beautifully unified. Among all the consequences of special relativity, none is more famous, or more profound, than the equation E equals mc2. With this compact formula, Albert Einstein revealed a truth that reshaped science, technology, and even world history. Mass and energy are not separate entities. They are different forms of the same physical reality. Before 1905, mass and energy were treated as entirely distinct concepts. In classical physics, mass measured the amount of matter in an object, its resistance to acceleration, and its gravitational pull. Energy, on the other hand, described the capacity to do work, whether through motion, heat, or other processes. Although both were fundamental quantities, they belonged to different conceptual categories. Nothing in the physics of Isaac Newton suggested that mass could transform into energy or vice versa. Special relativity changed that understanding completely. Einstein's reasoning began with the recognition that the laws of physics must be the same in all inertial frames, and that the speed of light is constant. From these principles came the realization that the traditional formulas for energy and momentum needed modification at high speeds. In classical mechanics, kinetic energy increases with the square of velocity, but as an object approaches the speed of light, its behavior no longer follows Newton's equations. Instead, its energy grows far more dramatically. When Einstein examined how energy behaves for objects moving at relativistic speeds, he discovered something remarkable. Even an object at rest possesses energy. This rest energy is proportional to its mass. The proportionality constant is the square of the speed of light, denoted by c2. Thus, E equals mc2. In this equation, E represents energy, m represents mass, and c is the speed of light in a vacuum approximately 300 kilometers per second. Because c is such an enormous number, and because it is squared, even a tiny amount of mass corresponds to an enormous amount of energy. This insight was revolutionary. It implied that mass is simply a concentrated form of energy. Matter is not fundamentally different from energy. It is energy in a highly compact state. To grasp the scale of this relationship, consider a small amount of mass, just 1 gram. If completely converted into energy, it would release an amount equivalent to the explosion of thousands of tons of TNT. The reason is the factor C2, which is extraordinarily large. The equation reveals a hidden reservoir of energy contained within every particle of matter. Einstein's conclusion was not speculative. It followed logically from the mathematics of special relativity. As objects gain kinetic energy, their total energy increases. In relativistic physics, mass and energy are part of a unified framework. The conservation of energy and the conservation of mass merge into a single principle, the conservation of mass energy. In nuclear reactions, this principle becomes dramatically visible. When atomic nuclei split or fuse, the total mass of the resulting particles is slightly less than the mass of the original particles. The missing mass has not vanished. It has been converted into energy, precisely as described by E equals mc2. This mass-to-energy conversion underlies nuclear power plants and nuclear weapons. Although Einstein did not directly develop the atomic bomb, his equation provided the theoretical foundation for understanding how immense energy could be released from small amounts of matter. During the Second World War, the implications of mass-energy equivalence became tragically clear. Yet beyond its technological consequences, E equals mc2 carries deep philosophical significance. It dissolves the rigid boundary between matter and energy. In classical thinking, matter was solid and substantial, while energy was abstract and dynamic. Special relativity shows that these are simply different expressions of the same underlying reality. Mass is not an independent substance. It is a form of energy bound into particles. Even a stationary object contains vast internal energy. The fact that we do not see this energy released in everyday life is because converting mass entirely into energy requires specific physical conditions, such as nuclear reactions. Einstein later expanded this idea within the broader framework of modern physics. In quantum field theory, particles themselves are excitations of underlying fields. Mass and energy appear as properties of these excitations. The boundary between thing and process becomes blurred. Another important aspect of mass-energy equivalence is that it changes how we understand inertia. In classical physics, mass is a measure of resistance to acceleration. In relativistic physics, energy contributes to inertia. As an object gains kinetic energy, its resistance to acceleration increases. This is why no object with mass can reach the speed of light. As it accelerates and gains energy, its effective inertia increases, requiring ever more energy for further acceleration. Approaching light speed demands infinite energy, making it physically unattainable. Thus, E equals mc2 is not merely an isolated formula. It is part of a larger relativistic structure. It explains why the speed of light is a universal limit. It connects mass, motion, and energy in a unified framework. The equation also deepens our understanding of the universe itself. Stars shine because of mass-energy conversion. In the core of the Sun, hydrogen nuclei fuse to form helium. A small amount of mass is converted into radiant energy, which travels across space as sunlight. Every ray of sunlight warming Earth is evidence of E equals mc2 in action. This realization connects the smallest particles to the largest cosmic processes. The same principle governs atomic nuclei and stellar furnaces. Matter throughout the universe carries within it the potential for extraordinary energy. Perhaps the most astonishing feature of E equals mc2 is its simplicity. In 5 characters, it captures a transformation in our conception of reality. It shows that what appears solid and permanent is, at a deeper level, dynamic and energetic. Matter is frozen energy. Energy is liberated matter. Through this insight, special relativity expanded far beyond the study of motion. It revealed an intimate unity between mass and energy, reshaping physics at every scale. The equation stands as a symbol of modern science, elegant, powerful, and transformative. In recognizing that mass and energy are interchangeable, Einstein did more than solve a theoretical puzzle. He unveiled a hidden truth about the fabric of existence itself, that beneath the surface of matter lies a vast ocean of energy, bound by the speed of light and governed by the principles of relativity. When Albert Einstein introduced special relativity in 1905, it was born not from a laboratory experiment, but from deep theoretical reasoning. Yet science ultimately demands experimental confirmation. A theory, no matter how elegant, must confront measurement and observation. Over the past century, special relativity has not only survived such scrutiny, it has been confirmed with extraordinary precision and has become essential to modern technology. One of the earliest confirmations came from studies of high-speed particles. As physicists began accelerating charged particles to enormous speeds in laboratories, they noticed behavior that classical physics could not explain. According to Newtonian mechanics, the relationship between force and acceleration is straightforward. But as particles approached the speed of light, they resisted acceleration more strongly than expected. Their momentum increased more rapidly than classical formulas predicted. These results matched exactly the predictions of special relativity. As velocity increases, time dilation and the relativistic relationship between energy and momentum alter the behavior of moving objects. The closer a particle moves to light speed, the more energy is required to accelerate it further. This is why no particle with mass can ever reach the speed of light. It would require infinite energy. Another striking confirmation involves unstable subatomic particles known as muons. Muons are produced when cosmic rays collide with atoms high in Earth's atmosphere. They are inherently unstable and decay in a very short time, only a few microseconds in their own rest frame. Given this brief lifetime, classical reasoning suggests that most muons should decay long before traveling the many kilometers required to reach Earth's surface. Yet detectors at ground level observe large numbers of muons. The explanation lies in time dilation. From the perspective of observers on Earth, the muons are moving at speeds close to light speed. Their internal clocks run more slowly relative to us, allowing them to survive long enough to reach the ground. At the same time, from the muon's own frame of reference, the distance through the atmosphere is length, contracted, making the journey shorter. Both perspectives are consistent within special relativity, and both match experimental results precisely. Perhaps one of the most elegant demonstrations of relativistic time dilation occurred in experiments involving atomic clocks. In the 1970s, highly precise atomic clocks were placed aboard commercial airliners and flown around the world. Identical clocks remained on the ground for comparison. When the airborne clocks returned, they showed slight differences in elapsed time compared to the stationary clocks. The differences were tiny, fractions of a microsecond, but they matched the predictions of special relativity with remarkable accuracy. These experiments demonstrated that time dilation is not theoretical speculation. It is a measurable, physical reality. Moving clocks tick more slowly. This has profound practical consequences in our modern world. A clear example is the Global Positioning System, commonly known as Global Positioning System. GPS satellites orbit Earth at high speeds. Because of their motion, the atomic clocks on board experience time dilation. If engineers ignored relativistic effects, GPS calculations would quickly become inaccurate, leading to positioning errors of several kilometers. To maintain accuracy, the system must account for special relativity, adjusting the satellite clocks accordingly. Every time a smartphone calculates a location, it relies on corrections predicted by Einstein's theory. Particle accelerators provide further confirmation. Facilities such as CERN accelerate particles to velocities extremely close to light speed. The design and operation of these machines depend directly on relativistic equations. Without accounting for time dilation, length contraction, and the relativistic relationship between energy and momentum, their predictions would fail. Even in medical technology, special relativity plays a role. In radiation, therapy, and medical imaging techniques involving particle beams, precise knowledge of relativistic particle behavior is essential for accurate treatment planning. The mathematics of Einstein's theory ensures the correct calculation of particle trajectories and energies. Mass-energy equivalence, expressed in E equals mc2, also found dramatic experimental confirmation in nuclear reactions. In nuclear fission and fusion, small differences in mass correspond exactly to enormous releases of energy, just as the equation predicts. Nuclear power plants convert a tiny fraction of mass into energy to generate electricity. In the Sun and other stars, fusion reactions transform mass into radiant energy, sustaining stellar luminosity for billions of years. What makes these confirmations so compelling is their precision. Modern experiments test special relativity to extraordinary degrees of accuracy. The speed of light has been measured repeatedly and found invariant, consistent with Einstein's second postulate. No experiment has ever demonstrated a violation of this principle. It is important to note that special relativity applies specifically to inertial frames systems moving at constant velocity. When acceleration and gravity are involved, Einstein later extended his ideas into general relativity. Yet even within its domain, special relativity remains one of the most thoroughly tested theories in physics. The real-world applications of special relativity demonstrate something profound about science. a theory that began as a conceptual resolution to inconsistencies in electromagnetism has become foundational to modern engineering, communication, and high-energy physics. It guides the operation of satellites, particle accelerators, nuclear reactors, and advanced medical equipment. More than a century after its introduction, special relativity is not an abstract curiosity. It is embedded in the infrastructure of contemporary civilization. The devices that enable global communication and navigation operate in harmony with Einstein's equations. The journey from theoretical insight to technological necessity highlights the power of fundamental science. Einstein did not set out to invent GPS or nuclear power. He sought to resolve a conceptual crisis regarding the nature of space and time. Yet by uncovering deeper truths about reality, he laid the groundwork for practical innovations that shape everyday life. The experimental confirmation and technological applications of special relativity stand as enduring testimony to its validity. A theory born from thought experiments and logical reasoning has been verified across laboratories, particle detectors, satellites, and cosmic observations. In doing so, it transformed from a revolutionary idea into an indispensable pillar of modern science and technology. The impact of special relativity extends far beyond equations and laboratory experiments. When Albert Einstein revealed that space and time are not absolute, that mass and energy are interchangeable, and that the speed of light is a universal constant, he fundamentally reshaped our understanding of reality itself. Special relativity is not just a theory of motion. It is a revolution in how we perceive the very fabric of the universe. Before Einstein, the universe was viewed in terms of absolutes. Time flowed uniformly for everyone, everywhere. Space provided a rigid, unchanging stage on which events unfolded. Matter was distinct from energy, and the two were governed by separate laws. This world, was intuitive, deeply rooted in experience, and consistent with classical mechanics. It allowed humans to imagine a predictable, clockwork cosmos, where understanding the position and motion of objects meant understanding the universe itself. Special relativity dismantled this comforting picture. Space and time were no longer independent. Instead, they formed a unified four-dimensional continuum called spacetime. Distances between events and durations of processes depended on the observer's state of motion. What one observer perceives as simultaneous, another might perceive as sequential. A moving clock runs slower relative to a stationary observer, and a moving object shrinks along the direction of motion. These are not hypothetical possibilities, they are precise consequences of Einstein's postulates. By revealing the flexibility of space and time, special relativity forced a reconsideration of what we call reality. Observers in relative motion cannot agree on absolute measures of time and distance, yet all physical laws remain consistent within each frame. Reality is therefore relative, not in the sense of being subjective or illusory, but in the sense that measurements depend on context. This challenges the naive assumption that the universe has a single, observer, independent timeline. Mass-energy equivalence adds another layer of profound significance. Matter and energy are not fundamentally distinct. Mass is a concentrated form of energy. This realization transformed our understanding of nuclear processes and the energy contained in matter itself. From the fusion in stars to the fission in reactors, special relativity provides the framework for comprehending the immense power bound within atomic nuclei. In everyday life, the implications may not be immediately visible, but they govern the sun's light, the energy in food, and the principles underlying modern technology. Special relativity also influenced how physicists think about motion, causality, and limits. The speed of light is the maximum speed at which information or influence can travel. This limitation preserves causality, ensuring that cause precedes effect in all inertial frames. Unlike Newtonian mechanics, where instantaneous action at a distance seemed possible, special relativity imposes a cosmic speed limit, fundamentally constraining the transmission of energy and information. The theory's philosophical implications are equally far-reaching. It dissolves the classical notion of an objective now. Every observer has their own valid perspective of simultaneity. Reality is not a single, universal sequence of events, but a network of interwoven space-time experiences. This does not render the universe chaotic. Rather, it reveals a deeper order, one governed by the precise mathematics of space-time intervals and relativistic transformations. Special relativity also set the stage for further revolutions in physics. By clarifying the relationship between space, time, and energy, it paved the way for general relativity, in which Einstein extended the relativity principle to accelerated frames and gravitational fields. It also influenced quantum theory, particle physics, and cosmology. The unification of mass and energy inspired the study of high-energy particles and the structure of atomic nuclei. The recognition that time and space are relative reshaped our approach to space exploration, GPS technology, and modern electronics. Even in popular imagination, the effects of special relativity have captured the public's fascination. Time dilation, the twin paradox, and the idea that moving clocks slow down challenge our everyday intuitions and force us to confront the strangeness of the universe. Science fiction often dramatizes these effects in interstellar travel and near-light-speed journeys, but in reality, they are precisely measured phenomena, validated by decades of experiments. Special relativity also emphasizes the power of human thought. Einstein's discovery arose not from elaborate laboratory apparatus, but from pure reasoning, thought experiments, and logical deduction. By questioning fundamental assumptions about space, time, and motion, he demonstrated that conceptual clarity can reveal truths as profound as those obtained through observation. This intellectual approach underscores that understanding reality often requires challenging the familiar and thinking beyond direct experience. Furthermore, special relativity illustrates the interconnectedness of natural laws. The principles of invariance and symmetry govern not only mechanics, but also electromagnetism and particle behavior. The unity of space and time, the linkage between mass and energy, and the constancy of the speed of light are all interconnected consequences of the theory's postulates. What appears as separate phenomena in classical physics are understood in relativity as different facets of a single, coherent framework. The theory also inspires reflection on the limits of human perception. Our everyday experience operates at speeds far below light, where Newtonian mechanics is an excellent approximation. Yet the universe operates according to deeper principles that can seem counterintuitive. Reality, as revealed by special relativity, is more subtle and intricate than our senses suggest. Recognizing this opens the mind to a broader, more sophisticated understanding of the cosmos. Special relativity is therefore more than a collection of equations. It is a lens through which to view the universe. It reshapes concepts of motion, time, space, energy, and matter. It bridges the very small and the cosmic, connecting the behavior of subatomic particles to the structure of spacetime and the processes powering stars. Its predictions have been confirmed repeatedly, yet its philosophical and conceptual implications continue to provoke wonder and reflection. Ultimately, Einstein's theory teaches that reality is both stranger and more harmonious than classical intuition allows. Observers in different frames perceive the universe differently, yet the laws governing them remain universally valid. Mass and energy are inseparable. Space and time are woven together. The speed of light imposes an absolute limit while enabling consistent causality. This transformed our understanding of existence, showing that the cosmos is far more subtle, elegant, and interconnected than previously imagined. Through special relativity, humanity gained a new comprehension of the universe, a comprehension that is precise, experimentally confirmed, and intellectually profound. It challenges our perceptions, stretches our imagination, and provides a framework for countless scientific advancements. In reshaping our understanding of reality, Einstein did not merely alter physics. He altered how we conceive of the universe itself. Special relativity remains a cornerstone of modern science, a triumph of human thought, and a reminder that the deepest truths of reality often lie beyond the surface of everyday experience.